So we are back to reading the chapter 1 from the book of Wilson and Walker, Principles and Technique. So the buffer capacity, it can be seen from the Anderson and Hasselbalch equation that when the concentration, or more strictly the activity of the weak acid or base is equal, that acids and base are working equally, the ratio is 1. A upon B is 1 and the logarithm 0, so that pH is equal to pKa. So what was the formula? pH is equal to pKa plus log unionized form upon ionized form, right? This formula. But right now this logarithmic part is 0, so pH is equal to pKa. So now this is defined as the the ability of a buffer to resist a change in pH on addition of a strong acid or alkali. So what is the work of buffer? It is to negate any changes that is occurring during a reaction. If acids are added, the conjugate base will nullify them. If the bases are added, then the H plus ions or conjugate acids will nullify them. But the ability of a buffer to resist a change in pH on addition of a strong acid or alkali. So those were weak bases or weak alkalis, but now it is a strong acid or alkali is expressed by buffer capacity. So beta, this thing, this is defined as the amount of moles of acid base required to change the pH by 1 unit. अमाउंट कितना हम डालेंगे एसिड और बेस ताकि pH चेंज हो जाए बाय 1 यूनिट. सो बीटा इज इक्वल टू dB अपॉन dpH और माइनस dA अपॉन dpH. So dB and D are amount of base or acid respectively. This is base and this is amount of acid, and dpH is the resulting change in pH. So in practice, beta is largest when pH range pKa plus minus 1. Okay. Amount of base, this is important, amount of base or acid is the resulting change in pH. So we did that question. We're moving to the next part. How would you prepare 1 dm cube of 0.1 m phosphate buffer, pH 7.1, given that pKa squared of phosphoric acid is 6.8, and that atomic masses of this Na, P and O are this charge respectively. So what do we have to find? How would you prepare? Okay, the buffer will be based on the ionization. So we are given phosphoric acid will break down like this. Okay, H2PO4 minus will break down, like H plus HPO4 2 minus. It is pKa given. That means 1 H is going away. 1 H has gone away. This is number 2, not a squared. Now we understood why. If it was not, it was 1, so we could have taken H3PO4, right? But it is second one, So we are taking this, and it is 6.8, and will therefore involve the use of sodium, sodium dihydrogen phosphate, NaH2PO4. So sodium dihydrogen phosphate, oxygen is this, atomic masses, and sodium hydrogen phosphate. Applying the appropriate Henderson-Hindelsbach equation, it gives pH is 7.1, buffer pH is 7.1, this is pH is equal to pKa upon plus log deionized upon ionized. Isn't that unionized? Okay. Unionized and ionized form. So this is subtracted, we got this. Then using antilog we got this. Okay. Since the total concentration of the two species need to be 0.1 m, it follows that HPO4 2 minus must be this much and this must be this much. The molecular mass are this and this delta respectively, hence the weight of each required is this and this. This is so complicated. What will I do in my life if things are going to be like this? So anyways, so let's get out of this numerical section and we'll be reading the theoretical part once more, what we are here for. Selection of a buffer. When selecting a buffer of a particular experimental study, several factors should be taken into account. Number 1, select the one with pKa as near as possible to the required experimental pH and within the range pKa plus minus 1. As outside this range there will be too little weak acid or weak base present to maintain an effective buffer capacity. Number 2, select an appropriate concentration of buffer to have adequate buffer capacity for the particular experiment. Buffers are mostly commonly used in the range of 0.05 to 0.5 m. Ensure that the selected buffer does not form insoluble complexes with any anions or cations essential to the reaction being studied. Phosphate buffer contains two precipitate polyvalent cations, for example, and may be a metabolic or inhibitor in the reaction. So once more we use what is it here, we have to select a pKa with almost as near to the whatever pH, the experimental pH we have. The pKa can be plus minus 1 with the experimental pH as outside range. Okay, outside range should be too weak for weak acid, too little for weak acid base to represent and maintain it. Select an appropriate concentration of buffer. An appropriate concentration of buffer should be taken to have adequate buffer capacity for the particular experiment. Buffers are most commonly used in the range of this 0.05 to 0.5 pKa. And lastly, ensure the selected buffer does not form insoluble complexes. So it is a rather important requirement that it does not form any complexes, basically insoluble complexes with any anion or cation essential for the reaction being studied. Okay. And lastly, ensure that the proposed buffer has other desirable properties such as being non-toxic, able to penetrate membranes, and does not absorb in the visible or ultraviolet region. Okay. Measurement of pH, the pH electrode. The pH electrode is an example of ion selective electrode that responds to one specific ion in solution in this case hydrogen ion. Responds to one specific ion. The electrode consists of a thin glass porous membrane sealed with the end of the hard glass tube containing 0.1 m hydrochloric acid, into which is immersed a silver wire coated with silver chloride. The silver chloride electrode consists of thin porous membrane sealed in the end of the hard glass tube containing 0.1 m hydrochloric acid, which is immersed silver wire coated with silver chloride. Okay, the silver chloride acts as an internal force that generates a constant potential. Okay, the porous membrane is typically 0.1 mm thick. The outer and inner 10 mm consist of a hydrated gel layer containing exchange binding site of hydrogen and sodium ions. On the inside of the membrane, the exchange sites are predominantly occupied by hydrogen ion from the hydrochloric acid, whilst on the outside the exchange ions are occupied by sodium and hydrogen ion. The bulk of the membrane is a dry silicate layer in which all exchange sites are occupied by sodium ions. Most of the coordinated ions in both hydrated layers are free to diffuse into the surrounding solution, while the hydrogen ion in the test solution can diffuse in the opposite direction, replacing bound sodium ions in process called ion exchange equilibrium. Any other type of cations present in the test solution are unable to bind to the exchange site, thus ensuring the high specificity of electrode. Note that hydrogen ions do not diffuse across the dry glass layer, but sodium ions can. Thus, effectively, the membrane consists of two hydrated layers containing different hydrogen ion activity separated by sodium ion transport system. The principle of operation of pH electrode is based upon the fact that there is a gradient of hydrogen ion activity across the membrane. This will generate a potential, the size of which is determined by hydrogen ion gradient across the membrane. Moreover, since the hydrogen ion concentration on the inside is constant due to the use of 0.1 m hydrochloric acid, the observed potential is directly dependent on the hydrogen ion concentration in the test solution. In practice, a small junction or asymmetry potential is also created in part as a result of linking the glass electrode to reference electrode. The observed potential across the membrane is therefore given by an equation that E is equal to E star plus 0.059 pH. Since the precise composition of the porous membrane varies with time, so too does the asymmetric potential. This contributes to the need of the frequent recalibration of electrode commonly used using two standard buffer of known pH. For each tenfold change in the hydrogen ion concentration across the membrane equivalent to a pH change of 1 in the test solution, there will be a potential difference change of 59.2 mV across the membrane. The sensitivity of pH measurements is influenced by the prevailing absolute temperature. The most common form of pH electrodes are the glass electrode and the combination of electrode, which contain an inbuilt calomel reference electrode. So this is a glass tube, glass electrode. So this is a shielded insulated cable. This is a glass stem, inner electrode, silver or silver chloride wire, a hydrochloric solution of 1 m, thin walled glass bulb. Another is combination electrode. It also has hydrogen chloride 0.1 m, glass membrane. It has a porous plug external reference electrode, a salt bridge solution using KCl, AgCl, silver or silver chloride internal electrode. Now we have other electrodes. Electrodes exist for the measurement of many other ions such as lithium, potassium, sodium, calcium, chlorine and nitrate in addition to hydrogen ion. The principle of operation of these ion selective electrodes is very similar to that of pH electrode in the permeable membrane specific for the ion to be measured and measure are used. They lack absolute specificity. Of this selectivity is expressed by selective coefficient that expresses the ratio of response to the competing ions relative to that of the desired ion. Most ISEs have a good linear response to the desired ion and a fast response time. Biosensors are derived from ISEs by incorporating an immobilized enzyme into the surface of the electrode. An important example is glucose electrode that utilizes glucose oxidase to oxidize glucose in the test sample to generate hydrogen peroxide that is reduced at the anode, causing a current to flow that is then measured amperometrically. Microsensor versions of these electrodes are of great importance in clinical biochemistry laboratories. The oxygen electrode measures molecular oxygen in solution rather than an ion. It works by reducing oxygen at the platinum cathode that is separated from the test tube by an oxygen permeable membrane. The electrons consumed in the process are compensated by generation of electrons in the silver anode. Hence, the oxygen tension in the test sample is directly proportional to the current flow between the two electrodes. Optical sensors use the enzyme luciferase. Okay, there's an enzyme called luciferase to measure ATP by generating light and detecting it with a photomultiplier. Quantitative biochemical measurements, analytical reconsideration and experimental errors. Many biochemical investigations involve the quantitative determination of concentration and or amount of a particular component, the analyte, present in a test sample. For example, in studies of the mode of reaction of enzymes, transmembrane transport and cell signaling, the measurement of the particular reactant or product is investigated as function of range of experimental conditions and the data used to calculate kinetic and thermodynamic constants. These in turn are used to deduce details of mechanisms of the biological processes taking place. Irrespective of the experimental rationale for undertaking such quantitative studies, all quantitative experimental data must first be questioned and validated in order to give credibility to the derived data and conclusions that can be drawn from them. This is particularly important in the field of clinical biochemistry, in which quantitative measurements on the patient's blood and urine samples are used to aid a clinical diagnosis and monitor the patient's recovery from a particular disease. This requires the experimental data to be assessed and confirmed as an acceptable estimate of the true values by the application of one or more standard statistical tests. Evidence of the validation of quantitative data by the application of such tests is required by the editors of referred journals for the acceptance for publication of draft research papers. The following sections will address the theoretical and practical consideration behind these statistical tests. Selecting an analytical method. The nature of quantitative analysis to be carried out will require a test to be taken on the analytical techniques to be employed. A variety of methods may be capable of achieving the desired analysis, and decision to select one may depend on variety of issues. These include availability of specific pieces of apparatus, the precision, accuracy, and detection limits of the competing methods, the precision, accuracy, and detection limit acceptable for the particular analysis, the number of other compounds present in the sample that may interfere with the analysis, the potential cost of the method, particularly important for representative analysis, the possible hazard inherent in the method and appropriate precautions needed to minimize risk, the published literature method of choice, personal preference. The most common biochemical quantitative and analytical method are visible, ultraviolet and fluorometric spectrometry, chromatography, chromatographic techniques such as HPLC and GC coupled to spectrophotometry or mass spectrometry, ion selective electrodes, and immunological methods such as ELISA. Once a method has been selected, it must be developed on or validated using the approaches discussed in the following section. If it is to be used for a prolonged period of time, measures will not need to put in place to ensure that there is no drift in response. This normally entails an internal quality control approach using reference test samples covering the analytical range that are measured each time the method is applied to test samples. Any deviations from the known values of these reference samples will require the whole batch of test samples to be reassayed. The nature of experimental errors. Every quantitative measurement has some uncertainty associated with it. This uncertainty is referred to as experimental error, which is a measure of difference between true value and the experimental value. The true value normally remains unknown except in cases where a standard sample, that is one of known composition, is being analyzed. In other case, it has to be estimated from the analytical data by the methods that can be discussed later. The consequences of the existence of experimental errors is that the measurements recorded can be accepted with a high, medium, or low degree of confidence depending upon the sophistication of the technique employed, but seldom, if ever, with absolute certainty. Experimental errors may be of two kinds: systematic error and random error. Systematic error, also called as determinate error. Systematic errors are consistent errors that can be identified and either eliminated or reduced. They are most commonly caused by a fault or inherent limitation of the apparatus being used, but may also be influenced by the poor experimental design. Common causes include the misuse of manual or automatic pipette, the incorrect preparation of stock solution, or incorrect calibration and use of pH meters. They may be constant, that is, have a fixed value irrespective of the amount of test annihilate present in the test sample under investigation, or proportional, that is, the size of the error is dependent upon the amount of test annihilate present. Thus, the overall effect of the two types is in a given experimental result will differ. Both of these types of the systematic error have three common causes: analytical error, instrument error, method error. This is best minimized by good training and or by automation of the method. Instrument method, this may not be eliminable, and hence an alternative method should be considered. Instrument error may be electronic in origin or may be linked to matrix of the sample. Method error, this can be identified by comparison of the experimental data with that obtained by the use of alternative methods. Identification of systematic error. Systematic errors are always reproducible and may be positive or negative, and that is they increase or decrease the experimental value related to the true value. The crucial characteristic, however, is that their cause can be identified or corrected. There are four common means of identifying this type of error: use of a blank sample, use of a standard reference sample, use of a alternative method, use of external quantitative and quality assessment sample. So we are identifying the systematic errors uh, with using a blank sample. This is a sample that contains none of the analyte under test, so that the if the method gives a non-zero answer, then it must be responding to some unintended way. The use of blank samples is difficult in case where the matrix of the test sample is complex, for example serum. The use of standard reference samples. This is a sample of test analyte of known composition, so the method under evaluation must reproduce the known answer. Alternative method. If the test or the alternative methods give different results of the given test sample, then at least one of the method must have an inbuilt flaw. This is a standard reference sample, external quality assessment sample. This is a standard reference sample that is analyzed by other investigators based on the different laboratory employing the same or different methods. Their results are compared, and any differences in excess of random errors similar identify the systematic error of each analyte. The use of external quantity assessment schemes is standard practice in a clinical biochemistry laboratories. Random error, also called the intermediate error. The random error are caused by unpredictable and often uncontrollable accuracies, and various manipulations involved in the method. Such errors may be variable, positive and negative, and are caused by the factors as difficulty in the process of sampling, random electrical noise in the instrument, or by the analyst being inconsistent in the operation of instrument or in recording readings from it. Standard operating procedure. The minimization of both systematic and random errors in essential in cases where the analytical data are used as the basis and crucial diagnostic and prognosis decisions is common. For example, in routine biochemical investigations and in the development of a new drug. In such cases, it is normal that the analysis to be conducted in accordance with the standard operating procedures that define in full detail the quality of the reagent, the preparation of standard solution, the calibration of instrument, and the methodology of the actual analytical procedure which must be followed. Assessment, or it is not assessment of accuracy. This is assessment of precision. It's like I'm preparing for a viva or something like that. Assessment of precision of analytical data set. Assessment of accuracy on an analytical data set. Value of proof, rejection of outliers, validation of analytical method, the use of t-tests, identification of prior outliers, validation of analytical method, comparing the method critical value, comparison of two analytical methods using replicated analysis, of test sample, calibration method, comparison to analytical method using different test samples, internal standards, safety in laboratory. So now we are going to do an overview. I'm not going to read line by line. Assessment of performance of an analytical method. So performance indicator that define how selected method perform under a specified condition. Knowledge of these performance indicators allow the analyst to decide whether or not the method is acceptable of the particular application. The major performance indicators: precision, also called precision or measure the reproducibility of the particular set sample. It very high degree. The measurement of set is high precision or low precision. In contrast of the high of values diverse, the measurements are said to be of poor or low precision. In analytical biochemical work, the normal aim is to develop a method that is as high precision as possible within the general objective of the investigation. However, precision commonly varies over an analytical range and over periods of time. As consequences, the precision may be expressed as either within batch or between batch. Within batch precision is the variability when the same test sample is analyzed repeatedly during the same batch to analyze the same data. Between batch precision is the variability when the same test sample is analyzed repeatedly during different batches of the analysis over a period of time. Since there is a more opportunity in analytical condition to change the assessment between batch and precision, it is higher of the two types of assessment. Results that are of higher precision may nevertheless be poor estimate of the true value, that is low accuracy or high bias, because of the precision and unidentified errors. Method of the assessment of the precision of a data set are discussed below. The term imprecision is preferred in particular by clinical biochemists, since they believe that it best describes the variability that occurs in the replicated analysis. Number 2, accuracy. There's a difference between the mean of the set. There's a difference between the mean of the set and the analytical measure of the same sample of test analyte and the true value of the test samples. As previously pointed out, that true value is normally known except in case of a standard measurement. In other cases, accuracy has to be assessed indirectly by use of an internationally agreed reference method or by the use of external quality assessment schemes and or by the use of population statistics that are discussed. Detection limit, also called sensitivity. This is the smallest concentration of the test analyte that can be distinguished from zero, that with a defined degree of confidence. Concentration below this limit should simply be reported as less than detection limit. All methods have their individual detection limits for a given analyte, and this may be one of the factors that influence the choice of the specific analytical method of a given study. Thus, the Barford, Lowry, and bichinonic acid methods for the measurements of the proteins have detection limit of 20, 10, and 0.5 microgram protein centimeter cube respectively. In clinical biochemical measurements, sensitivity is often defined as the ability of the method to detect the analyte without giving false negatives. Sensitivity is often defined as the ability of the method to detect analyte without giving false negatives. Analytical range. This is a range of concentration of the test analyte that can be measured reproducibly. The lower end of the range can be of the detection limit. In most cases, the analytic error is defined by an appropriate calibration curve. The precision of the method may vary across period. Analytical specificity, also called selectivity, sensitivity, selectivity. There are differences. Okay. This is a measure of the extent to which other substances that may be present in the sample of the test analyte may interfere with the analysis and therefore lead to a false high or low value. A simple example of the ability of a method to measure glucose in the presence of other hexose such as mannose and galactose. In clinical biochemical measurements, selectivity is an index of the ability of the method to give consistent negative results for known negatives. Analytical sensitivity. This is a measure of the change in response of the method to a defined change in the quantity of the analyte present. In many cases, analytical sensitivity is expressed as the slope of linear calibration curve. Robustness. This is a measure of ability of method to give consistent results in spite of small changes in experimental parameters such as pH, temperature, amount of reagents added. For routine analysis, the robustness of a method is of practical consideration. This form also indicate that indicators are established by the use of well-characterized tests and references analyte sample. The order in which they are evaluated will depend on the immediate analytical priorities, but initially three most important may be specificity, detection limit, and analytical range. Once the method is in routine use, question of assuring the quality of the analytical data by implementation of quality assessment procedure comes into play. Assessment of precision. After quantitative study has been completed and the experimental value of the amount or concentration of the test analyte in the sample obtained, the experimenter must ask the question, how confident can I be of the result that is acceptable of true value? Is it accurate? In addition to the question, maybe is the quantity of my analytical data comparable with the published scientific literature for a particular analytical method? That is it precise? Once the answer to such questions are known, the result has high probability of being correct and accepted and used as a basis of the design for the studies, whilst the result of these methods unacceptable error can be rejected. Unfortunately, it is not possible to assess the precision of the single quantitative determination. Rather, it is necessary to carry out the analysis in replicate, that is, experiment is repeated several times of the same sample of test analyte, and to subject the resulting data set to some basic statistical tests. If a particular experimental determination is repeated numerous times and a graph constructed of the number of times a particular result occurs against its value, it is normally bell shaped, with result clustering symmetrically above mean value. This type of distribution is called Gaussian or normal distribution. In such cases, the precision of the data set is the reflection of the random error. However, if the plot is skewed in one side of the mean value, the systematic errors have not been eliminated. Assuming that the data set is of normal distribution time and there are three statistical parameters that can be used to quantify precision. Standard deviation, coefficient of variance, and variance. Standard deviation, coefficient of variation, and variance. Measure of precision. These three statistical terms are alternative ways of expressing scatter of the values within the data set about mean calculated by summing the total values and dividing the number of individual values. Each term of the has its individual merit, and in all three cases the term is actually measuring the width of the normal distribution curve, such as the narrower the curve, the smaller the value of the term and the higher the precision of the analytical set. The deviations of the data set is a measure of variability of the population from which the data set was drawn. It is calculated by the use of equation, this standard deviation. Or this another standard deviation. Xi minus x stars is the difference between the individual experimental value and the calculated mean of the individual values. Since there is a difference, maybe positive or negative, and hence the distribution of the experiment value about the mean is symmetrical. If they were simply added together, they would cancel each other out. The differences are therefore squared to give the consistent positive value. To compensate for that, the square root of the resulting calculation has to be taken to obtain the standard deviation. Remember the n minus 1. Standard deviation has the same units as an actual measurement and is one of its attraction. The mathematical nature of the normal distribution curve is such that 68.2% of the area under the curve is within one standard deviation either side of the mean. 99.5% of the area under the curve is within two standard deviations, and 99.7% three standard deviation. Exactly 95% of the area under the curve falls between the mean and 1.96 standard deviation. The precision or imprecision of the data set is commonly expressed as plus minus 1 st of the mean. The n minus 1, the term n minus 1 is called degree of freedom of the data set and is an important variable. The initial number of degrees of freedom possessed by the data set is equal to the number of results in the set. However, when another quantity characterizing the data set, such as mean or standard deviation, is calculated, the number of degree of freedom of the set is reduced by 1 or by 1 again for each new derivation made. Many modern calculators or computers include programs for the calculation of standard deviation. However, some use variants of equations 1.10 in that they use n as a denominator rather than n minus 1 as the basis of calculation. If n is larger than 30, for example, then the difference between the two calculations is small. But if n is small and certainly is, if it is not less than, then the use of n is rather the use of n rather than n minus 1 will significantly underestimate the standard deviation. This may lead to the false conclusions being drawn from the precision of the data set. Thus, for most analytical biochemical studies, it is imperative that the calculation of standard deviation is based on the use of n minus 1. Coefficient of variance, CV, also known as relative standard deviation of the data set, is the standard deviation expressed as the percentage of mean shown in this is CV, coefficient of variance, S into 100% upon x bar. X bar is the mean. Since the mean and the standard deviation have the same units, the coefficient of variance is simply a percentage. This independence of the unit of measurement allows methods based on different units to be compared. Variance, lastly, of the data set is the mean of the squares of the difference between each value and the mean of the values. It is also the square of the standard deviation, hence the symbol S square. It has units that are the square of the original units, and it makes it appear rather cumbersome, which explains why standard deviation and coefficient of variance are preferred ways of expressing the variability of sets. The importance of variance will be evident in later discussion when making a statistical comparison. To appreciate the relative merits of standard deviation and coefficient of variance as measures of precision, consider the following scenario. Suppose the two serum sample A and B were each analyzed 20 times for serum glucose by glucose oxidase method, such that sample A gave a value of 2 mm with standard deviation 0.1 mm, and sample B a mean of 8 mm and a standard deviation of 0.41 mm. On basis of the standard deviation value, it must be concluded that the method that had given the better precision for sample A than B. However, this ignores the absolute values of the two samples. If this is taken into account by calculating coefficient of variance, the two values are 5% and 5.1% respectively, showing that the method has shown the same precision for both samples. This illustrates the fact that standard deviation is an acceptable assessment of the precision given for the given data, but it is necessary to compare the precision of the two or more data sets, particularly one that has different mean values, and then coefficient of variation should be used. Okay. The majority of well-developed analytical methods should have a coefficient of variance within the analytical range less than 50%. Less than 5%. And many especially automated methods of less than 2%. 1.4.4 Assessment of accuracy. Population statistics. Let me see. Assessment of accuracy. Population statistics. While standard deviation and coefficient of variance give a measure of variability of the data set, they do not quantify how well the mean of the data set approaches the true value. To address this issue, it is necessary to introduce the concepts of the population statistics and confidence limit and confidence interval. If a data set is made up of a very large number of individual values, so that the n is a large number, then the mean of the set would be equal to the population mean, mu, mu. The standard deviation will be equal to the population standard deviation, sigma. Note that the Greek letters represent the population parameters and the common alphabets of the sample parameters. These two population parameters are the best estimate of the true values, since they are based on the largest number of individual measurements, so that the influence of the random errors is minimized. In practice, the population parameters are seldom measured for observation for obvious practicality reasons, and the sample parameters have a large uncertainty associated with them. The uncertainty of the sample mean deviating from a population mean decreases in the proportion, and the reciprocal of the square root of the number of values is set. Thus, to decrease the uncertainty by a factor, there is a factor by two number of experimental values would have to be increased fourfold, and for a factor of 10 the number of measurements would need to be increased 100-fold. The nature of this relationship again emphasizes the importance of evaluating the acceptable degree of uncertainty and the experimental result before the design of the experiment is completed and the practical analysis begun. Modern automated analytical instruments recognize the importance of the multiple results by facilitating repeat analysis at maximum speed. It is good practice to report the number of measurements on which the mean and standard deviations are based, as this gives a clear indication of the quality by the calculated data. Let me see this question. Assessment of the precision of the analytical data set. Question is, 5 measurements of fasting serum glucose concentration were made on the same sample taken by a diabetic patient. The values obtained were 2.3, 2.5, 2.2, 2.6 and 2.5 mm. Calculate the precision of the data. So we'll add it all and divided it by 5, and which is giving me 2.42 mm. Now we'll find the standard deviation of it. So standard deviation is mean minus the current data. Okay, we'll sum it up, and then squared it up and sum it up and square of the xi's and its sum. Okay, the standard deviation is equal to under root of xi minus x dash square n minus 1. That is what formula is used here, which is giving me this using question. Okay, now this is a different equation. Let me see, 1.11. okay, this is the 1.11. This is a good, normally we do not use it. So this is the summation of xi squares minus summation of xi square. Okay, do you understand this? Upon n minus 1, and whole is under rooted. So xi squares under root of xi squares minus wait a second, once more into it. Summation of xi squares minus summation of xi square into divided by n upon n minus 1 under root. Isn't that 8? Yes. Okay, so it is used, and we find this. So both are s only, both are standard deviation only, and it is close. So we are using 0.165. It's 4, it's 6, so we are using the middle value of it. We are finding CV. CV is S into 100% upon x bar. We are getting 6.82% discussion. In this case, it is easy to appreciate the precision of the data set by considering the coefficient of variance. The value is 6.82 is moderately high for this type of analysis. Automation of this method would certainly reduce it by at least half, so that the legitimate to quote that the answer to these questions calculation to one more digit than was present in the original data set. In practice, it is well to carry the statistical analysis on a far larger data set than presented in this example. Now let's continue. Confidence intervals in confidence limit and student's t factor. Except that the population mean is the best estimate for the true value. The question arises: how can I relate my experimental value, experimental sample mean in the population mean? The answer is to use the concept of confidence. Confidence level expresses the level of confidence expressed in the percentage that can be attached to the data. It has a value to be set by the experimenter to achieve the objectives of the study. Confidence level is a mathematical statement relating to the sample mean to the population mean. A confidence interval gives a range of value about the sample within which there is a given probability. Determine the confidence. The relationship between two means is expressed in the terms of standard deviation of the data set. The square root of the number of values in the data set is known as the student's t. This where x bar is the mean, u is the population mean, s is the measured standard deviation, n is the number of measurements, t is the student's t factor. The term s divided by under root of n is the standard error of the mean and is measured by the precision of the sample mean. Unlike standard deviation, standard error depends upon the sample size and will fail as the sample size increases and will fall. The two standard measurements are sometimes confused, but in essence, standard deviation should be used if we want to know how widely scattered the measurements and standard error should be used if we want to indicate the uncertainty around a measurement, around a mean measurement. The confidence level can be set up to the value of 100%. For example, it may be that the confidence level of only 50% would be acceptable for a particular experiment. However, a 50% level means that there is a chance, of 1 in 2 chance that the sample mean is not an acceptable estimate of the population mean. In contrast, the choice of 95% or 99% confidence mean would mean that there would be 1 in 20 or 1 in 100 chance respectively that the best estimate had not been achieved. In practice, more analytical biochemists choose confidence range between 90 to 99% and most commonly 95%. Students T is a way of linking probability with a size of data set and is used in number of statistical tests. Students T value for varying numbers of data set and hence that is selected at the confidence level of ability statistical test. Some values are shown in table 1.7. So this is the table, the confidence level, and this is students T. So if we have degree of freedom 7 and we are taking 95% accuracy, so students T is this. Okay. The numerical value of T is equal to the number of standard errors of the mean that must be added and subtract from the mean to give the confidence interval of the given confidence level. Note that as sample size and hence the degree of freedom increases, the confidence level converge. If when n is large and we wish to calculate 95% confidence interval, the value of T approximates 1.96 and some text code equation in this form. The term student's T factor may give the impression that it was devised especially with students' needs in mind. In fact, student was the pseudonym of the statistician by the name of W.S. Cossett, who in 1908 first derived the term, who was not permitted by his employer to publish his work under his own name. So sad. Criteria for the rejection of outlier experimental data, Q-test. A very common problem in quantitative biochemical analysis is the need to decide whether or not a particular result is an outlier. Should therefore be rejected before the remainder of the data set are subjected to a statistical analysis. It is important to identify such data as they have disproportionate effect on the calculation of mean and standard deviation of the data set. When faced with this problem, the first action should be to check the suspected outlier is not due to the experimental or mathematical error. Once the suspect figures out once the suspect figure has been confirmed, the validity is checked by application of Dickson's Q-test. Like other tests can be to be described later. The test is based on null hypothesis, namely there is no difference in the value being conjured. If the hypothesis is proved to be correct and the suspect value cannot be rejected. Suspect value can be used to calculate the experimental rejection quotient. Q quotient is then compared with the tabulated critical rejection quotient. For a given confidence level, the number of experimental tests, if Q experiment is less than the Q table, the null hypothesis is confirmed and the suspect value should not be rejected, or if it is greater than the value can be rejected. The basis of this test is the fact that number distribution 99.5% for a value within our true range of deviation of mean. In setting limit of the accessibility of or rejection of data, the compromise has to be made on the confidence level chosen. If high confidence level is chosen, the limit of acceptability are set wide, and therefore there is a risk of accepting values that are subject to error. If the confidence level is set too low, the acceptability limit will be too narrow, and therefore there will be a risk of rejecting legitimate data. In practice, a confidence level of 90 or 95 is most commonly applied. The Q table values in table 8.1 are based on 95% confidence level. The calculation of QEXP is based on the question equation 1.14 that requires the calculation of separation of the questionable value from the nearest value, coupled with the knowledge of the range. QXP xn minus xn minus 1 upon xn minus x1 gap upon range. X values are investigation phase. So let's check out this question. Calculate the confidence of interval at 50%, 95% and 99% confidence level of the fasting serum group. So the previously calculated x is equal to this, s is equal to this. At 50% t value is this. The confidence interval will be that. Confidence interval is x plus minus this student's t into the standard deviation upon under root of n. So we'll be getting this. For 95% the t is this. We'll be putting t there and we'll be getting this. Okay. On 99% the student's t is this. So we'll be getting this. This is these calculations show that there is a 50% chance that the population mean lies in the range of 2.37 to 2.47. 50% chance show that the mean lies in the 2.22 to 2.62. And 95 shows that it lies between 2.09 to 2.75 mm. Whether the confidence level increases, the range of potential values and the population mean is also increased. You can calculate for yourself that if mean standard deviation is based on 20 measurements. Value of Q for rejection of outliers 4, 5, 6, 7, and 95% confidence. Okay, 1.4.5 validation of analytical method of use of t-test. A t-test in general is used to address the question as to whether or not two sets have same mean. Both data sets need to have a normal distribution and equal variance. There are three types: unpaired t-test, paired t-test, and sample t-test. Unpaired t-test used to test whether two data sets have same mean. Paired t-test used to test whether two data sets have same mean, where each value in one set is paired with the value of the other. One paired t-test used to test whether the mean of the data set is equal to a particular value. Is this question? If the data in set in example 5 of the condition outline point out 95%. So this is the gap and this is the range. Wherever symmetrical one will be fine is equal to this, and the Q experiment is smaller than the Q table, the point should be not be rejected. As there is more than 95% chance that it is a part of the same data, and such as the 5 symbols. Okay. Each test is based on null hypothesis, which is that there is no difference between means of the two data sets. Tests measure how likely the hypothesis is to be true. The attraction of such tests is that they are easy to carry out and interpret. Analysis of standard solution. One sample t-test. So t calculated is equal to known value minus mean into under root of n upon standard deviation. So critical values, the border between the difference between the levels. If t calculated is greater than t global, then accurate results are deemed not to be from the same data. So in the standard deviation of significant confidence. Estimated consideration is therefore drawn in an article that is not with standard solution, and is that there are unidentified reasons. You know, applying the analytical method to known test invalidate sample until the problem has been solved. Another question of standard this t calculated, we find the t calculated note the question. You have to comparing to competitive analysis and compare t plus basis 2 minus 2. Okay. Geometry formula for comparing with the quantitative stated with the person. However, if in doubt an F test, the official introducing the question which are responded to the words and the variance. This calculates the values of F is which is the ratio of the larger of the two variance and the smaller variance. Compare with the critical value available in statistical table. It is the critical values of F with a 95% confidence. The practitioner is calculated confidence in the table. So there are some formulas. We calculated x1 minus x1 S pool. Okay, S pool, how it's been found? It is this. T calculated, and we are finding T calculated. How to find degree of freedom is this. Where x and the calculated meaningless and the holds n into all the number of measurements to move at first sight is 4 equations. We are doubting but closing expectations that they are simply based on the variance and mean and the number of analytical measurements of the mathematical manipulation of the data related to it. Introduction to analytical replicated analysis of the single test sample. So x, s and s square, s, x bar, s and s square. F calculated is found. F is the higher standard deviation, larger variance, ratio of the larger variance upon to the smaller variance. So this is F calculated. F table of the set degree of freedom is so F calculator is less than F table, it can be the two variants are significantly different. Therefore, the use of this S pooled is this, T calculated is this, therefore it is to compare it. Pair T test and variant is another. So it's this and it is this. T is the difference between paired results. D bar is the mean difference between the paired results. N is the number of paired results. ST is the standard deviation of the difference between the pairs. 1.4.6 Calibration methods. Quantitative biomechanical analysis also involve the use of calibration curve produced by the use of known amounts of annihilate using the spectrum. The calibration curve is the record of the measurement, absorption, peak, area, etc. produced by the analytical precision and the response of the range of known quantities of the standard annihilate. It involves the preparation of standard deviation, standard solution of the annihilate and the use of a range of equalytes in the test analytical process. It is a good practice to replicate each calibration point and to use the mean plus minus standard deviation construction of the inspector. The compiled data usually reveals a scatter of the points about the linear relationship, but such that there are several options of the best fit. It means every fitting of the best fit by eye is not recommended by the highly subjective and is irreproducible. The method of least mean square linear regression is the most common mathematical way of fitting a straight line of data, but in implying method. It is important to realize that the accuracy or values of the slope and intercept that gives are determined by the experimental error built by into x and y values. The mathematical basis of LMSLR is complex and will not be considered here. But the principle upon which it is based are simple. It is a relationship between the two variables such as the concentration or amount of annihilate and response is needed. Then the best straight line will give general form y is equal to mx plus c, where x and y are the two variables and is so based on the calculation of comparison of the two analytical methods used. So take this, t gives the mean, it's the difference of mean added. Do the two methods give the same result? The standard, we find standard deviation with this. From the equation we use find t calculated. Now we'll be comparing it to the table. Alternative approach to the comparison of two slope, intersect, correlation. This will be see in the graph. Coefficient of determination. Stronger the correlation between the two, the closer the value of r approaches plus 1 or minus 1. The values of r are quoted over 4 decimal places. For the correlation commonly exceeds this. The value of 0.098 or less should be considered with care since even slight correlation values. This is goodness of it. Selection of the standard values. A range of standard annihilate amount of concentration should be selected in the probability so that the value are equally distributed along with the calibration curve. Test samples should not be estimated outside this range and there is no limitation. It's such point of registration profile. It is common for the precision to decrease inside a range at the end of the curve and it may be implication of a retention use of the curve. For example, intervention precision in a famous system requires the use of different methods since the two values and range test is in this formulas cannot be accommodated with excessive precision for the work on one calibration curve. There is a blank sample. There is one such that no standard analyte is present. One should be included in the experimental design when possible. Any experimental value, that is absorption, obtained for it must be deducted from all other measurements. This may be achieved automatically in spectrometric measurements by the use of double beam spectrophotometer, in which the blank sample is placed in this reference. A shape of the curve. It should not be assumed that all calibration curves are linear. They may be curved in the base representation with a quadratic expression of the type y is equal to ax squared b x plus c. constant recalibration. A new recalibration curve should be constructed in the calibration. It cannot be acceptable to rely on calibration curve produced by much earlier occasions. 1.4.7 Internal standards. An additional approach for the control of time-related minor issues an ideal internal standard of compound is that the molecular structure and the physical properties similar as possible, and the test and annihilate which gives similar response with an analytical method of test and annihilate. This response expressed in the unit quantity basis may be different from the unit for the test and annihilate, but provided that the relative response of the two compound is constant. The advantage of the use of the internal standard is not compromised. Quite commonly in the internal a known fixed quantity of the standard is added to each test sample. Internal standards are commonly used in liquid or gas chromatography since they help to compensate the small temporal variation of the flow of liquid and gas through the chromatographic column. In such application, it is of course essential that the internal standard chromatographs are near to but distinct from the test analyte. If the analytical procedure involves a preliminary sampling procedure such as solid phase extraction, it is important that the known amount of internal standard is introduced into the test sample at as early a stage as possible and is therefore taken through the preliminary procedures. This ensures that any loss of the test analyte during the preliminary stages will be compensated by identical losses in the internal standard, so that the fine relative response of the method of the two compound is true reflection of the quantity of the test analyte. Safety in 1.5 Safety in laboratory. Virtually all experiments conducted in a biochemistry laboratory present a potential risk to the well-being of the investigator. In planning any experiment, it is essential that careful thought be given to all aspects of safety before the experimental design is finalized. Health hazards come from a variety of sources. Chemical hazards. All chemicals are, to a very extent, capable of causing damage to the body. They may be irritants or cause a short-term effect on exposure. Alternatively, they may be corrosive or cause severe or often irreversible damage to the skin. Examples include strong acids and alkalis. Thirdly, they may be toxic once they have gained access to the body by ingestion, inhalation, or absorption across the skin. Once in the body, their effect may range from slight to extreme of being the poison, that is, example, cyanide, or carcinogen, example, benzene or vinyl chloride, or a teratogen, example, thalidomide. Finally, there is a special case of the use of radioactive compound that is discussed in detail in chapter 14. Number 2, biological hazards. Examples include human body fluids that may carry infections such as HIV, laboratory animals that may cause allergic reaction or transmit certain diseases, pathogenic animals and cell tissue cultures, and all microorganisms including genetically engineered forms. In the UK, animal experiments must be conducted in accordance to the Home Office regulation and guidelines. All experiments with tissue and cell culture should be conducted in microbiological cabinets that are provided with a sterile airflow away from the operator. Number 3. Electrical and mechanical hazards. All electrical apparatuses should be used and maintained in accordance to the manufacturer's instructions. Electrophoresis equipment present a particular potential for safety problems. Centrifuges, especially high-speed varieties, also need careful use, especially in the correct use and balance of the rotors. Number 4. General laboratory hazards. Common examples include syringe needles, broken glassware, and liquid nitrogen flasks. Routine precautions that should be taken to minimize personal exposure to these hazards include wearing the laboratory clothes, which should be the high-necked buttoned variety for work with microorganisms, safety spectacles and lightweight disposable gloves. It is also good practice not to work alone in laboratory, so that help is to hand if needed. In UK laboratories, work is subjected to legislation including Health Safety at Work 1974, a Controlled Substance Hazardous Health Regulation 1994, and Maintenance Management of Health and Safety at Work Regulation 1999. This legislation requires a risk assessment to be carried out prior to the undertaking lab work. As the name implies, a risk assessment requires potential hazard to be identified and an assessment made for the potential severity and the probability of occurrence. Action must be taken in case where such potential severity and probability are medium to high. Such assessments require knowledge of the toxicity of all chemicals used in the study. Toxicity data are widely available via computer packages and published handbooks and should be on reference in all laboratories. Once the toxicity data are known, consideration may be given to the use of alternative and less toxic compounds, or if it is decided to proceed with the use of toxic compounds, precautions taken to minimize the risk and plans laid for dealing with an accident should one occur. These include arranging access to first aiders and other emergency services. It is normal for all laboratories to have a nominated safety officer whose responsibility it is to give advice on safety issues. To facilitate good practice, procedures for disposal of organic solvents, radioactive residues, body fluids, tissue and cell culture, and microbial culture are posted in all laboratories. 1.6 Suggestions for further reading: Analytical methodology and quality assurance. Blah blah blah. Read it for yourself. I am tired. Chapter 1 is done. Next we'll be doing cell culture techniques, chapter 2, but not today. Bye bye.